Hey everybody, welcome back to the Joy of Coding at Portland State University. Computer programs don't exist in isolation. They transform inputs from some source into outputs that are delivered to some destination. These inputs and outputs can range from information provided by a person, to measurements gathered from a sensor, to data that is sent to another software system for further processing. I/O is fundamental to software development, and the Java programming platform contains APIs that leverage object-oriented design patterns for class hierarchies and object composition to provide powerful, flexible, and easy-to-use mechanisms for performing I/O. Let's dive in. So in this set of slides, we're going to talk about Java's facilities for working with data that is external to the running code. We'll look at APIs for working with files in a file system, and also for working with data that is in a byte format, so-called byte streams, and then text data with readers and writers. The classes and interfaces that we talk about in these slides are all in the java.io package, and there are a lot of facilities for performing I/O operations. There's the file class that represents a file, and we'll see some of the methods that you can use to get information about files. There are the stream APIs, which are all about performing byte-based I/O, and the readers and writers, which are all about working with text-based I/O. Let's take a look at the java.io file class. A file represents a file, and you can create a file object from the string, which is the name or location of the file, or from another file object that represents the directory that the file resides in, and then the name of the file inside that directory. And once you have one of these file objects that represents a file, you can call methods on it to get information about it. For instance, you can call canWrite to determine whether or not a file can be written to. You can perform some operations on the file, like deleting it, checking to see if it exists, or get some information about the file, like its name or whether or not it's a directory. You can also get its length. If you want the file to represent a directory, you can call the makedir method to create the directory. File also has a getParentFile method that will return the file object that represents the directory that contains this file. File also has some static fields, some class fields, that contain constant information related to files. So for instance, there's a field called separator, and it's also available as a separated char, which returns the string or character that separates portions of a file spec. So if you're running on a Unix machine, this field has the value /. Similarly, the path separator and path separator char fields store the string or character that separates directories in a path. So on Unix, this is the colon. The nice thing about these fields is that they abstract out the path separator and the file spec separator, so that your code can just reference these fields if they need those values, and then you know no matter what platform you're running on, the correct value for that platform will be provided. There are two interesting and important interfaces in the Java.io package called FileFilter and FileNameFilter. Each of these interfaces has one method called accept that returns Boolean and takes a file object, or sometimes a string, that will either accept or reject that input based on some criteria. These interfaces are used as arguments to the list and file list methods of file. So the list method of file takes a file name filter and will return the names of all of the files that are accepted by that file name filter. Similarly, list files takes a file filter and returns all the files in the directory represented by the file that's invoked on that are accepted by that file filter. Let's see how these interfaces are used in action. So at the top of the slide, we have an example of a file filter. This is a class called directoryFilter that implements the file filter interface. Because it implements file filter and it is not an abstract class, it must provide an implementation of the accept method. And this method simply returns whether or not the file that is provided to the accept method is a directory. At the bottom of the slide, we have an implementation of FileNameFilter. Its accept method takes two arguments, a file which represents the directory in which a file resides and the name of the file. And this implementation of accept merely determines whether or not the file name that's passed in ends with .java. So we have a directory filter that accepts directories and a Java file name filter that accepts files whose names end in .java. Here is a program that will find all of the Java files that descend from a given directory. It uses both a file filter and a file name filter in order to accomplish this. Let's first look at the main method to see where this program starts. First thing it does is it creates a new file object from the first argument that's passed in on the command line. This will be the directory in which we will look for Java files and then recurse into subdirectories. So we check to see if the file that is passed in on the command line represents a directory. If it is, great, we'll do some stuff. If it's not, in that else clause, we'll issue an error message because this program is meant to be run with a directory. But in the case that we do have a directory, we perform the following. We initialize some static variables, which are essentially global variables within this program, but they're private, so I guess it's okay. We set the directory filter to be the new directory filter object, whose class we saw on the previous slide. And similarly, we create a new Java file name filter and assign it to the Java filter static field, which is declared at the beginning of the class. Note that the types of the fields are the more abstract type. The type of dir filter is file filter. It doesn't need to be a directory filter because, as it turns out, the code that uses the dir filter, a static field, doesn't really care what kind of file filter it is. Same thing for file name filter. We use the more abstract type here, and that's something that you'll see a lot in this class. I call it programming to the interface. When you represent data, it often helps to have that data be represented as generically as possible. That way you're not locked into a particular implementation, and it helps take some of the cognitive burden off of the person who reads the code, because they don't need to know the specifics of the implementation. It also allows the implementation to change over time. Now let's take a look at that find Java files method. What does this do? It takes a directory, and the first thing that it'll do is print out the names of all of the files that end in .java that are in that directory, and then it'll recurse into the subdirectories. And here's how it does that. The first line in the method takes the dir that was passed in and invokes the list files method on it, providing the Java filter, the Java file name filter. And that will return an array of files whose names all end in .java. Then we'll simply iterate over that array and print out the name of the file. Then we want to recurse into subdirectories. The way we do that is that we take the directory that we're currently inspecting and call list files on that directory object, providing it the directory filter. This will return an array of files that contains all of the directories in that directory. Then we iterate over all of those directories, and we call find Java files recursively on each one of those directories. When we run this program, we see the following. So the first thing we do is we go to a directory that contains a bunch of Java source code, and then we'll run the program. We'll run the main command line argument, invoking the Java virtual machine, telling it the class path to look for is in /classes, and then the fully qualified name of the find Java files class, which I've abbreviated here. It's edu pdx cs410j io.findjavafiles, and we give it the current working directory, or dot, as the argument. And as you'll see, it then prints out all of the Java files that are under that directory. So why is this an interesting example? Well, in addition to performing some operations that are relevant to I/O, this demonstrates a very important pattern in object-oriented programming. If you go back and look at the definitions of the directory filter and the Java file name filter classes, you'll note that they don't have any state. There are no fields. All you have is one method and its implementation. In this case, we have a class, and we use instances of that class to encapsulate not state, but just pure behavior. There isn't any state. As a matter of fact, every instance of that class will be exactly the same. There is no unique state to it, and all the behavior is the same. But what this allows you to do is to have a really nice partition between the responsibilities for filtering files. So the file API, the implementation of the file API is responsible for knowing the low-level details of how to get at the files within a directory and how to work with the underlying file system. But it doesn't know what files are interesting. Instead, what it does is it delegates or abstracts that information to these interfaces. So the file class knows how to apply the filter, but it doesn't know which criteria to apply. Similarly, you know what you want to filter, but we rely on the file object to know about the underlying operating system, no matter what machine it runs on, to take care of all those low-level details. And so by separating these responsibilities, you have a nice clean delegation model where you know what behavior and responsibilities you have and what behavior and responsibilities the code that you're calling has. Now we're going to talk about some of the APIs for performing I/O, moving data in and out and sometimes in between parts of a Java program. So Java I/O contains two hierarchies of classes that work with bytes. These are called the stream APIs. There are classes for performing stream output, so byte output, and then for stream input. This is reading in byte data from a source and doing something with it. At the root of the byte output class hierarchy is an abstract class called output stream. And as you can see, there are a number of subclasses of output stream that perform various things. And we'll take a brief tour of these shortly. There's a corresponding hierarchy of input streams. These are classes that read bytes from some source and do something with it. And if you look closely, you can see that there's kind of a mapping, a matching of output streams and input streams. So what is an output stream exactly? Well, it basically is an abstract class that writes bytes to some destination. And it has methods like the following. Write. You give it a byte array and it'll write it someplace. Because it's abstract, output stream doesn't know exactly where you write that to. It could be a file, it could be a socket, it could be an internal memory buffer. It doesn't care, it just knows that it can write bytes someplace. You can also close an output stream, which will clean up any system resources and basically make it so you can't write to that stream anymore. And then also there's a flush method, which if there is any pending output that has been buffered up, it'll write those bytes to the underlying stream. So this is a really great foundational class which provides a good abstraction over writing bytes to some destination. We saw on the previous slide there's a whole hierarchy of output streams. Here are a couple of highlights. There's a byte array output stream, which provides the output stream interface to writing to a byte array, a buffer in memory. There's piped output stream, which is used in conjunction with a piped input stream to send data between threads. Basically, it's like a Unix pipe. And then there's a class called object output stream, which will take any object and the primitive types and write them to some byte stream. This uses a process called serialization, which is beyond this set of slides, but maybe we'll talk about it later in the course. A couple other examples of output streams that I want to dive into in a little bit more detail. A file output stream writes bytes to a file. And so then here you can create a file output stream from a file object, or it's the name of a file. When you create a file output stream, it might throw a file not found exception. For instance, if you try to create a file output stream for a file whose directory doesn't exist, you'll get a file not found exception. So you can imagine file output stream is used a lot whenever you want to write to files. Another interesting subclass of file output stream is Java I/O filter output stream. A filter output stream performs some filtering on bytes before ultimately delivering them to another output stream. So for instance, there is a class called buffered output stream, which will buffer the bytes of data up into chunks of a certain size before sending them off to some other destination. So let's say you want to buffer data before writing it to a socket or something. You can use a buffered output stream for that. Another kind of filter output stream is a thing called a data output stream, which writes Java's primitive types in a format that is machine independent. If you're dealing with like big endian, little endian, and things like that, this comes in really handy. And finally, another kind of filter output stream, which you may recall you've seen before, is a thing called a print stream. And so a print stream is meant to write data to a bunch of bytes in a human-readable format. And it's intentionally easy to use. It doesn't throw exceptions when you go to interact with it. Print stream is the type of system.out and system.error. So when you access the system.out object, what you're really doing is invoking methods of print stream. And so printstream is the class that provides the print and printline methods that can be used with any type of data ranging from an int to an object. Now, just because it doesn't throw exceptions doesn't mean that problems can't occur. And if you want to see if a problem has occurred with your print stream, you can invoke the hasError method to determine whether or not something's gone wrong. So here's an example of using output streams. And what we're going to do in this program is we're going to take a bunch of numbers, double floating point numbers, from the command line and write them to a file in a binary format. And we're going to use some of the Java I/O APIs to do this. The first line of our write doubles class is the declaration of a static field called err, which will hold a reference to system.err as a print stream. This is just an example to show you once again that system.err is a print stream. Looking at our main method, the first thing that we do is take the first argument and create a file output stream that will write to that file specified by the first argument. So we have a variable called FOS, which is of type file output stream, and then we initialize it. We assign the value of a new output stream with the name that's in the first argument to that FOS variable. Creating this file output stream might throw a file not found exception, and so we have to catch it. And when we do, we print a message to the system.error, and then we exit the program by calling system.exit1. If we have successfully created our file output stream, then what we're going to do is we're going to write the doubles from the remaining command line arguments to that file output stream. Now, if you look at the file output stream API, it doesn't have a method that lets you write a double to it. You can just write bytes to it. However, if you look at the data output stream API, it is the thing that writes doubles to some destination. And so what you do is you create one of those data output streams, and when you invoke its constructor to initialize the object, you pass in your file output stream. So what you're doing is wrapping a data output stream around your file output stream object. And then the rest of the program, what it does is it iterates over the remaining command line arguments, tries to parse each one of them as a double. That gets you a little d double value. And then it invokes the write double method on the data output stream. Writing a double to the data output stream converts that double into bytes, which are ultimately written to the file output stream that is wrapped in the data output stream. Now, while you're performing these operations, some things might go wrong. So for instance, if there is an argument on the command line that does not represent a valid double, a number format exception will be thrown, and we'll catch that and handle it appropriately by printing an informational message. Similarly, while you are writing to the data output stream, some I/O exception could occur, and if it does, we will catch that, print an error message, and then do a system.exit. So you would run this program like the following. You would invoke the write doubles main method. You would provide arguments like doubles.out, which will be the name of the file to which the double values are written, and then provide some double values like 123, 2.34, 3.45. Now, assuming the program runs successfully, you could look at doubles.out, and if you were to do so, you would see that it's binary, right? It's garbage. There's nothing printable there because what you wrote was double values, the binary values of those doubles. While this isn't human readable, it's also perfectly machine readable and it's very compact. So beyond demonstrating how to use these Java I/O APIs to write doubles to a file, this example shows some interesting object-oriented design patterns. So as we saw, this program delegates behavior to multiple objects. So ultimately what we want to do is write a double to a file. And we use several objects all working together to accomplish this goal. So when we write the double to the data output stream in turn converts that double to a byte array, which is written to the file output stream, which then is ultimately written to the file itself. So I like to think of these objects working together as sort of like an onion, right? We're only dealing with the outside of the onion, the data output stream. But if you start peeling things back, you'll see that inside the data output stream is a file output stream. And if you peel that back, you'll see that inside that is a file. So here's a way that objects can all work together. But the code itself, that loop that wrote the doubles, it didn't really care that the double ultimately was going down to a file. It just wrote it out to a data output stream. So now let's talk about input streams. This is taking bytes from some source and processing them. So an input stream is the abstract superclass of all these different types of input streams. And they read bytes. So they will read bytes into some byte array. You can invoke methods on the input stream like available, which returns the number of bytes that can be read without blocking, like how many bytes are left in the file. You can close the stream when we're done with it, and that'll clean up the resources, the underlying resources associated with that stream. The read method reads bytes into a byte array, and it's overloaded to take some different arguments. And its return value is the number of bytes that were read, or if all of the bytes have been read, then -1 is returned. And as you're reading in bytes from the stream, you can call skip to skip over some number of bytes. And this kind of thing can be a nice optimization as you're processing binary data. Some subclasses of input streams which are interesting. There's the byte array input stream. So this provides the input stream behavior, the ability to read bytes at a time over a byte array, so an in-memory buffer. Again, there's piped input stream, which is used in concert with a piped output stream to send data in between threads. And there's also something called a sequence input stream, which you give it multiple input streams, and it'll read the first one, the second one, the third one, etc., in a given order. You can imagine that you've got a very large piece of data that maybe you spread over multiple files. This way you can have what we'll see a file input stream for each one of those files, but a single sequence input stream that'll just read it from beginning to end across all files. As I just referred to, there is a Java I/O file input stream that will read bytes from a file. And just like the file output stream, you can create it from a file object or from the file's name. And again, if there isn't a file that I can read from, it'll throw a file not found exception. We saw the filter output stream. There's also a filter input stream that will read bytes from an underlying data source and do some processing on them before delivering them to the read method of the filter input stream. So for instance, there's buffered input stream, which reads input from another input stream. There's a data input stream, which is used to read primitive types in Java. There's something called pushback input stream, which allows you to read some bytes and then push them back into the stream so they can be read again later. If you've looked at look-ahead parsers and things like that, you can imagine you would use this class to implement something like that. In the output stream section of the slides, we saw an example class called write doubles. This is its equivalent, read doubles. Again, we start with a couple of declarations of fields, just for example. These are print streams, so we have one for system.err and system.out. And then we have our main method, which takes one argument, which is the name of a file, and from that file, it will then read all the double values in it. So here we create our file input stream. Again, we pass in the name of the file that we want to read from. If that file can't be found, it'll throw an exception, and we will handle it appropriately. Then we create a data input stream. Data input stream is the class that provides read double. It is the thing that can read a double from some other input stream. In this case, that other input stream is the file input stream that we created. And then we'll iterate reading doubles until we can't read doubles anymore. Then we call the read double method on the data input stream. We get the value of the double. We will print it out to standard output with a space after it, and then call flush, which will push it all the way to its final destination, which is standard output on the terminal. If while attempting to read a double, an end of file exception is encountered, that's okay, not the end of the world in this case. We simply break from the loop and are done with the program. If another type of I/O exception occurs while reading the double, that's more serious. We'll print out the error message and then call system.exit to exit the program. Finally, after we've read all of the doubles, we'll just print an empty line and call it a day. If we were to run this read doubles program with the doubles.out file that we created a few slides ago when we wrote doubles, you'll see that it prints out 1.23, 2.34, and 3.45. Exactly the same values that we provided to write doubles. So a couple of things about this program that I wanted to point out. In the data input stream, you don't have a good way of saying whether or not it's done. You might be able to call available. I don't know if that would necessarily always work. So you have to catch the end of file exception. It's not super pretty, but it works. And also, I purposefully in this example used the print method and the flush method. When you have these filter output streams, like print stream, if you want to see the output right away, you must explicitly call flush. Because by design, these filter output streams can perform some buffering and caching at their discretion. So one of the things I've had to do sometimes is, as I'm adding debugging output or as I'm generating something to a file, explicitly flush all the data out there so they can see it and interrogate it. So we saw the output stream and input stream APIs for handling byte data, and they do that really well. But a lot of the data that we work with is in a text format, and the byte-based streams, you can make them work for that, but it's a little awkward because you have to do a lot of data encoding, and really when you want to deal with characters and strings, if you work with just the stream APIs, then you have to do a lot of conversion back and forth. There's another set of APIs called the writers and the readers that look a lot like the streams. I think they can say that they have a lot of similarities, but their APIs are designed for working with text. So again, you've got two class hierarchies. You have the writers that have an abstract superclass called writer that writes text to a destination. Similarly, you have readers that read text from some source. So Java I/O writer has a write method that writes characters or a string. It's overloaded that way. And has a close and a flush, just like you saw with the stream APIs. Some examples of writers: something called a buffered writer, which will buffer up some text before writing to its destination. You can write to a character array that underlies it. And so the whole idea is that you write some text to this char array writer, and then you can get the underlying character array and work with it that way. Filter writer is an abstract class that filters text before it's written to some other destination. And for you fans of the piped input stream, piped output stream, yes, there is a piped reader and piped writer. And then one writer that is pretty useful is something called output stream writer. And what this does is it is a writer that converts the characters that is sent to that writer to bytes and then writes those bytes to some output stream. And what output stream writer does is it forms a bridge between the two APIs. It is a writer that works with the stream APIs, which is something that you want to do a lot, especially when you've got a print stream like system.error. Here are some more in-depth descriptions of other kinds of writers. There's something called a print writer, and what it does is it prints text and formats it nicely to a writer or to an output stream. Print writer is the class that has the print and print line APIs. But note that unlike print stream, it doesn't automatically flush to its destination. You have to either enable auto flushing or explicitly call the flush method. String writer provides the writer API and writes to a string in memory. So this is nice. So this gives you the ability to use the writer API to build up a string that you can work with just like any other string. It's actually implemented using a string buffer, and you can get access to that string buffer object if you'd like. Or you can just call the toString method on the string writer to get the string that you've been building up with that writer. And of course, there's a file writer that writes text to a file. And you can create a file writer by giving a file object or by providing the file's name. Here's an example that writes a text from the command line to a file. In this example, we'll have a static field called air, which is of type print writer. And this is just an example. As we see in the first executable line of the main method, we initialize that air field with the value of a new print writer that is wrapped around system.air. And the second value provided to the constructor is true, which means that it should automatically flush its contents at the end of every call to print. Inside that try block is where the interesting stuff in the program happens. We create a new file writer for writing to the file specified by the first command line argument. And then we iterate over the rest of the command line arguments and write that value to the writer object and provide a new line in between each of them. Once we're done writing all the command line arguments, we flush the writer and then we will close it. If any I/O exceptions happen while performing these operations, we print out an error message. And when we run this program and provide the arguments text.out for the name of the file, and then the command line arguments, this is some text, as 4 additional command line arguments, we run the program, and if we look at the contents of the text.out file, we'll see that it is the value of the command line arguments, each on their own line. Beyond just demonstrating how to write text to a file, this example also showed how you can wrap a print writer around a print stream. In this case, the print stream was system.error. We wrapped a print writer around it. And again, this object composition provides an abstraction that ultimately simplifies programming because you don't have to worry about what's actually going on. Again, that code that just wrote to the print writer, it didn't care where its final destination was. It had one job, and all its job was to write some text to some writer, doesn't care where it goes. The whole idea is that the code, and therefore the coder or the person reading the code, doesn't know where they're writing to, and more importantly, they don't care. This abstraction simplifies programming and takes the cognitive load off of the programmer. We learned about writers. Here's similar information about readers. The readers are rooted in a reader class, which is the abstract superclass for all of those reader classes. And all a reader does is it reads character data from some source. So it's got methods like read, which will read a bunch of characters. It has a method that returns Boolean, determining whether or not it's ready for more text to be read. You can close it, and then you can skip over some number of characters in any reader. Many of these example readers are analogs to writers that exist out there. So there's a car array writer that has a character array reader, which allows you to read from any character array. There's the abstract superclass of readers that perform some filtering on character streams before delivering it to its final destination. Piped reader and pipe writer. And string reader, which provides the reader interface over a string. And again, we see something like input stream reader, which provides a bridge between the reader and writer APIs and the stream APIs that allows you to read character data from an input stream. And then there's buffered reader, which will buffer the text as you read it and deliver it to the read method. Buffered reader is the class that has the read line method. So if you want to read a line from a file, from standard input, or any source, you would use a buffered reader because it's the thing that has the logic to go read ahead enough characters until you find the end of a line and then deliver that line to the caller. And we'll use buffered reader here in this example, which reads text from the console. Probably in your CS 101 course, the way you provided data to a program was through standard input. Right? Your program will sit there and wait until the user types something on the terminal and hit return, and then it read that line that was input from the user. Well, here's how you do that in Java. And I'm going to warn you, it's not terribly natural because, well, these days people don't write too many programs that read from standard input. But here's how you can do it. In the main method from this read from console, the first thing we do is we create an input stream reader around system.input. So remember, system.in is an input stream that reads from the terminal, from the command line. We don't want to read bytes, because that's what input streams do. We want to read characters. And so the way you read a character is with a reader object, and you use an input stream reader to read from some input stream. So we wrap an input stream reader around system.in, and now we have something that we can use to read characters from system.in. Now, we don't want to read just characters. We want to read an entire line of characters. So we use the class that's good for reading lines of things, which is buffered reader. And so then we create a buffered reader around that input stream reader. And this then lets us read a line of text. We'll also use a string writer to store the lines that we read from standard input. Now, this is just for an example. I don't know if you'd really do it this way, but we have this here as an example of how to use the string writer class. Now, what are we going to do? Well, we'll just sit there and loop until the user enters -1 on the command line. We invoke readLine from our buffered reader. We say br.readLine. What is this going to do? Well, it's going to read a line. Where's it going to read a line from? It's going to read a line from the input stream reader. Where's that input stream reader going to read its text from? It's going to read it from bytes from standard input. And so this is how we accomplish the goal of reading a line from standard input. We're going to read that line. It'll be returned as a string. And if the string equals -1, great, we're done here. We're going to break from this loop. Otherwise, we're going to write that line to our string writer by invoking the write method on our text object. So it'll read each line there until -1 is entered. And of course, if anything goes wrong, if any IO exception occurs, it'll print out an error message and exit. And finally, there at the end, it will print out the value of the string writer that has been built up in the loop. So if we run this program and we provide the following into standard.input, we say does hit return this program work, and then -1. It will then print out the lines of text that have been entered that aren't -1. Does this program work? Once again, we've seen a couple of things. We've seen the very practical way of reading a line of input from standard in. That's great. We've also seen how the Java I/O API uses object composition to accomplish these goals by having all these objects that do individual things have their own very focused responsibilities that can be put together and arranged in a way so that you can accomplish something like reading a line of data from standard input. Now, when working with I/O, it's very important that we clean up after ourselves. Many I/O operations deal with resources that are outside of the direct control of the program, things like files and network sockets and connections to other devices. If after working with these external entities, if you don't properly clean up, the program will end up holding on to additional resources that take up space, might prevent other programs from accessing it. It's just bad form. This is why the streams and the readers and writers all have close methods. These close methods often terminate the underlying connection, release the file back to the operating system, close the network socket so that its memory can be reclaimed, all that kind of stuff. So it's very important that you do that. However, it's often easy to forget to call close on these objects, especially if you end up passing the objects around to other methods and things like that. So here is a method called printTextFile, which uses some very common patterns for cleaning up I/O objects once you're done with them. The first thing that it does is it creates a buffered reader around a new file reader for the file that you want to print, and then iterates over each line of the buffered reader and prints it out. And hey, if there's any I/O exception, then it prints out a message and then rethrows it. And then the finally block, if your buffer reader actually was created in the first place, then it'll call close and clean up. This code works. This code is fine, but I don't know about you, but I always forget that finally block, right? I always forget to close my readers and writers once I'm done with them. Luckily, there is a language feature that makes it a lot more difficult to forget to close your streams. There's a variation of the try statement called try with resources. After the try keyword, you can provide a series of statements that create objects that are auto-closed. So the whole idea is at the end of the try block, the objects are automatically closed out. And by the way you determine whether or not an object can be automatically closed is if it implements the auto-closable interface. So here's another version of that same printTextFile method that uses the try with resources language feature. Instead of creating your buffered reader outside of the try block, you create it sort of inside the try block. You say try, and then you give it an expression in parentheses. So that's where you create your buffered reader, same buffered reader. And then inside the try block, once again, you would read over each line of the buffered reader. Then if there was an exception, yep, you would catch it and print it out. Actually, I think if you want the examples to be exactly the same, you would also rethrow the exception. But here, you don't need that finally. The Java runtime will automatically keep track of which objects are auto-closable, and before this method returns, regardless of how it exits, will invoke the close method on all those auto-closable objects. And now you, as the programmer, don't need to remember to call the close method on the reader. So that's an introduction to Java's I/O APIs. As I hope you saw, there are a number of tools available for externalizing data that is outside of your running code. A lot of the time you'll be working with files on a file system, and the Java I/O file object does a great job of representing that. When it comes to moving data in or out or even between parts of a Java program, there are two APIs for doing that. If you're dealing with byte data, you'll want to use the stream APIs like output stream and print stream. If you're working with text data, you'll want to use the readers and the writers. Those are things like file writer, buffered reader, etc. So that's it for now. I hope this information gets you off to a good start working with Java's APIs for performing I/O, which you'll use in many of the assignments here in the Joy of Coding at Portland State University.